Salam, peace be upon you. My name is Mohammed Layiq Sediqi, the father of Holophase. Part 20: Spectral Modes as Abstract Basis. Remember the language we are learning. There is one field, phi, the holophase, one continuous cyclic movement from which all of reality unfolds. When phi begins to change, its first derivatives appear, and with them, the three dimensions show themselves at once: time as omega, space as k, and motion as v, built from both. Every higher derivative is a finer question about how phi changes, and each one casts three shadows together: a time shadow, a space shadow, and a motion shadow. These echoes mix and weave into one another, forming the patterns we call fields, particles, bodies, thoughts, and worlds. In this picture, everything that exists is a living tapestry of phi, endlessly echoing through its derivatives and their dimensional shadows. Today, we listen to just one of those echoes. We are in Episode 8, the pure abstract language. We are completing book 8.5, which is called Abstract Semantics. In this book, we have been asking a very deep question. How does the language of phi carry meaning before there is any particular universe to describe? We have seen how meaning can arise purely from relationships inside the language itself. We have understood the triunity of time, space, and motion as three simultaneous projections of one underlying structure. We have introduced quadratic forms as a way of measuring intensity, the how much of change. We have discovered action as the principle of optimality in this language, the way the field prefers some stories over others. Today we arrive at the final semantic layer of this episode. We ask how any story that phi tells, no matter how complex, can be taken apart and rebuilt from simpler, purer components. We meet spectral modes as abstract basis, the idea that every pattern of phi can be understood as a blend of fundamental tones of structure. Spectral here simply means about the spectrum of patterns, and basis means a set of building blocks from which anything can be made. Let us begin with something you can easily feel. Imagine you are sitting in a grand concert hall. An orchestra is playing a rich, emotional symphony. At first, what reaches your ears is one continuous ocean of sound. The violins, the cellos, the horns, the flutes, the drums, the whole ensemble have melted together into a single living wave of music that rises and falls and moves you. Now imagine you had a special gift of hearing. With this hearing, you could listen inside the sound and separate the symphony into clear strands. You could follow only the violins and hear their bright line, even while everyone else is playing. You could tune into the deep hum of the double basses. You could isolate the sharp voice of the flute or the soft heartbeat of the timpani beneath everything. The symphony is still one piece of music, but now you can recognize it as a particular combination of many pure ingredients. These pure ingredients are like modes. A mode is a simple repeating pattern that can exist by itself. The whole orchestra sound is a sum of many modes. In the same way, a complicated pattern of phi can be seen as a sum of pure patterns, each with its own character. Spectral modes are those pure patterns. You can see the same idea in space. Picture the outline of a long, wavy coastline seen from above. At first glance, it looks irregular and complicated. Big bays, smaller inlets, fine jagged edges, and rocky details. But a mathematician can express that coastline as a sum of waves drawn along the shore. There are very long, gentle waves that set the overall bend of the coast. There are medium-sized waves that carve bays and headlands. There are very fine, high-frequency ripples that create the tiny roughness. The coastline is just one way of adding all those waves together with different strengths. Again, we have a complicated pattern that can be rebuilt from simpler, repeating modes. This gives us the key insight for this part. Any pattern can be seen as a superposition of simpler patterns. Any configuration of phi can be decomposed into spectral modes, and any configuration of phi can be reconstructed from those modes. The messy whole is just a particular chord played on a deep, abstract instrument. Where does this sit in our language picture? Earlier, we spoke of derivatives like omega and k as forming an alphabet of change. Those letters told us how phi evolves in time and space. They picked out how fast, how steep, how curved, how accelerated the field is in each dimension. That was like learning the letters that describe motion and deformation. Spectral modes go deeper. They are like the pure letters of shape itself. Think of a written alphabet. The letter A is a pure shape. The letter B is another pure shape. Each letter by itself does not tell a story, but every story you ever write in that language uses those letters. In the language of phi, a mode is like one of these letters, but spread out across space and time. A single mode is a clean, simple pattern of phi over the whole domain. A full story that phi tells is like a long word or a sentence made by adding many modes together with different amplitudes. So we can say it this way. Spectral modes are basis elements of the phi language. Any pattern of phi can be synthesized by adding modes with certain strengths and phases. And any pattern of phi can be analyzed by asking how much of each mode it contains. An abstract basis is just a set of such pure components, out of which every possible configuration can be built, at least to any desired accuracy under reasonable mathematical conditions. Let us now say what a mode is in more scientific but still simple language. A spectral mode is a special configuration of phi that behaves in a very neat way under differentiation. When you take derivatives of a mode with respect to time or with respect to space, or in both together, you often get back something that is proportional to the same pattern. The shape of the mode survives, only its overall size or phase changes. If we describe this in words of an equation, we would say a certain differential operator acts on the mode and gives back a number times the same mode. The operator is a machine that asks questions like, how curved are you here? How much do you accelerate in this direction? How much do you change when I move slightly in time or space? The number that comes out is called an eigenvalue, and the pattern that survives is called an eigenfunction. You do not need to remember those terms. What matters is that a mode is a pattern that, when questioned in a particular way, simply answers, I remain myself, just scaled by this factor. This property makes modes extremely powerful. When we expand the complicated configuration of phi into modes, we are really saying, this messy pattern is just a combination of self-consistent patterns, each with its own characteristic scale or frequency. The complicated becomes understandable because we know the personality of each mode. Now listen to this through our three echoes: time, space, and motion. In the time echo, temporal modes are pure rhythms, like simple sine waves with a single frequency. Any complex time signal, such as a musical note, the daily pattern of your heartbeat, or the voltage in a circuit, can be expressed as a sum of these pure rhythms. In the space echo, spatial modes are pure shapes, like the standing wave patterns on a guitar string or the vibrational patterns of a drum skin. Any complex spatial configuration of vibration can be decomposed into these shapes. In the motion echo, dynamical modes describe patterns that move and evolve while preserving their identity, such as a traveling wave that keeps its shape while it propagates, or a standing wave that oscillates in place. The crucial point is that this decomposition is not a trick we are making up. Under very general conditions, it is a mathematical fact. Functions on suitable spaces can be expanded in terms of basis modes. In familiar cases, this is just the Fourier series or the Fourier transform. In other cases, it is a different family of modes. But the song remains the same. The space of possibilities comes with a natural set of structural notes. Let us play spectral modes back into the master tree. We have imagined phi as a tree with a trunk and branches. The trunk is the value of phi itself. The first branches are its first derivatives, the appearance of omega, k, and v. Higher branches are the higher derivatives, curvature, acceleration, higher twists and bends. Sigma, winding, knots, braids, and holonomy live in the way whole trees and forests are arranged, the global topology. All of this describes the shape of a particular configuration. The spectral modes are not another branch. They are not a fruit. They are more like the mineral content of the soil from which every tree grows. The soil beneath the forest contains different nutrients. Every tree that grows in that soil is one way of drawing those nutrients up and arranging them into form. In the same way, the set of spectral modes is like the full list of pure patterns that the underlying space will allow phi to express. Any specific configuration of phi is one choice of how strongly each of these patterns is activated. Spectral modes are also deeply connected to almost everything else we have introduced. When you look at derivatives in the model basis, things become simpler. For many operators, applying a derivative to a mode just multiplies that mode by some factor or mixes it with a small family of related modes. Asking how do you change or how curved are you becomes easy to answer in the model language. Equations that look like complicated differential equations in real space often turn into simple algebraic relations between mode amplitudes. The same happens with intensity. Quadratic forms like omega squared and the square of the spatial gradient become very transparent when expressed in modes. Each mode has an amplitude, which tells you how strongly that mode is present. The intensity of that mode is often just proportional to the square of its amplitude times some characteristic factor related to its eigenvalue. The total intensity in a configuration can be written as a sum over modes. This tells you how the energy-like quantities are distributed among different scales and patterns. Action, the quantity that the language uses to judge which stories are preferred, also becomes clean in the model basis. In many important cases, the action separates into independent contributions, one for each mode. The difficult problem of finding the optimal history of phi becomes a collection of simpler problems, one for each mode amplitude. It is like listening to the orchestra and discovering that, for the purpose you care about, each instrument can be studied separately because the score respects a hidden structure. Constraints and symmetries also speak naturally in the language of modes. Boundary conditions select which modes are allowed and which are forbidden. A string that is fixed at both ends can only support standing waves that vanish at the endpoints. Rotational symmetry around an axis selects certain families of spatial modes and kills others. In this way, the symmetries of the situation act as a filter on the modal alphabet, choosing which letters can actually appear in the story. What does all this mean semantically? It means the language of phi has a built-in power to analyze and to build. Spectral modes let the language analyze any complex story by asking which modes are present and how strongly. They also let the language build new stories by choosing a set of modes and assigning amplitudes. This is exactly what we do when we think scientifically. Faced with a complex phenomenon, we look for repeating structures, dominant rhythms, and characteristic scales. Once we find them, we construct models as combinations of those modes and see how well the models match reality. You can think of spectral modes as both microscope and toolbox. As a microscope, they let you zoom into different scales of a pattern, separating coarse features from fine details. As a toolbox, they give you simple pieces that you can assemble into very complex structures without losing control of what you're doing. In the Holophase language, this power is not bolted on from the outside. It comes for free from the way phi lives on spaces that support modal decomposition. Now let us talk briefly about stability and limits. The careful claim is that for the kinds of fields we care about, defined on suitable spaces with enough smoothness, any physically meaningful configuration can be approximated as well as we like by a sum of spectral modes. We do not claim that a small number of modes always suffice. We claim that by including more and more modes, we can approach the pattern arbitrarily closely. If we ever found a phenomenon where this idea truly failed, it would teach us something important. Perhaps the field did not really live on a smooth manifold. Perhaps the natural basis was not the simple eigenmodes we chose, but a more subtle family, like wavelets or modes adapted to fractal structures. In that case, the holophase framework would not collapse. It would simply have to generalize what counts as a mode and what counts as a basis. The core idea that phi's patterns can be understood as combinations of simpler structural tones would remain intact. To make all of this less abstract, let us visit a few examples. When you pluck a guitar string, you are exciting a mixture of harmonic modes. The string does not vibrate in a random way. It vibrates as a combination of the fundamental mode, with one big bump, plus higher harmonics with more bumps. The tone you hear depends on how much of each mode is present. In a quantum atom, the allowed stable electron states are spatial modes in the potential around the nucleus. Any general state can be written as a superposition of those orbitals. In image compression, a photograph is decomposed into basis patterns, and only the most important modes are kept. In all these cases, modes are the real working vocabulary behind the scenes. You can even feel a loose analog in human culture. A culture expresses itself through common melodies, rituals, ways of greeting, stories it tells again and again. These are like cultural modes. Any particular festival or gathering is one mixture of those modes with different strengths. Studying the modes gives you insight into the culture. Recombining them lets the culture create new events that still feel like themselves. This is only an analogy, not physics, but it helps us sense what it means to think modally. You can also practice seeing modes in daily life. When you hear a musical tone, try to listen for the pure pitch and its faint, higher overtones. When you look at the patterned fabric, try to separate the large repeating motif from the smaller decorative details and the tiny textures. When you watch waves on water from two different sources, notice how simple circular waves combine into a more complex interference pattern. Each of these is your nervous system intuitively doing spectral analysis. Before we close, I want to deepen one more layer that will help you feel why spectral modes belong to the same unified vision as winding, knots, braids, and holonomy. All of these ideas might sound like separate chapters. Modes belong to harmonic analysis, winding to topology, braids to world lines, holonomy to connections. But in the holophase view, there are different faces of one thing: the way phi organizes change and shape across scales. Think again of a vibrating drum. You can tap the drum in any messy way you like. Very soon, the motion settles into a mixture of a few clear modes, the natural drum patterns. Those modes are distinguished by their frequency and their spatial shape. If you watch the drum for a long time, you may find that energy slowly shifts from one mode to another. The pattern of which modes are active and how strongly is like a sentence in the language of modes. Now add topology to this picture. Suppose the drum head has a small defect, a tiny region where its material properties are different. That defect acts like a sigma region for the effective field describing the vibration. Some modes will be especially sensitive to it, others will avoid it. The presence of the defect can shift which modes are favored and which are suppressed. In this way, the topological and geometrical features of the system are reflected in the modal spectrum. You could, in principle, learn about the defect just by listening to the overtones. This is exactly the kind of unity the Holophase program is aiming at. One story told in several accents. The same idea appears in much grander settings. Think of the cosmic microwave background, the faint afterglow of the Big Bang spread across the sky. Cosmologists decompose its temperature variations into spherical harmonic modes, the natural spectral basis on a sphere. Each mode carries information about structure at a particular angular scale. The whole sky becomes a spectrum of modes. From that spectrum, scientists infer the shape, age, and composition of the universe. Here again, an almost unimaginably complex pattern becomes legible when written in the alphabet of modes. Or zoom down into the brain. Neural activity is messy and high-dimensional. But when researchers place electrodes on the scalp or inside the brain, they often talk about alpha rhythms, beta rhythms, gamma rhythms, and so on. These are rough, biological versions of spectral modes. A given mental state or behavioral pattern does not activate just one rhythm. It is a blend of several. The brain's activity is like a choir of oscillations, and different thoughts or states correspond to different chords in that choir. Once again, a modal view makes complexity intelligible. Even the climate of the Earth can be studied this way. Temperature, pressure, and wind patterns across the globe can be decomposed into large-scale modes like El Niño patterns, planetary waves, and smaller regional oscillations. Particular weather events are messy, but the climate as a whole reveals preferred modes of variation. Understanding those modes helps us see how local events are tied to global structure. You can begin to sense a repeated message. When we want to understand complex extended systems, we almost always end up doing some form of spectral thinking, whether we use that name or not. In the Holophase picture, this is not just a lucky analytic trick. It is the natural way the one field phi expresses itself. Modes are not only convenient for us, they are part of phi's own internal organization. In effect, phi comes with its own preferred basis of expression. When the universe writes with phi, it automatically writes in combinations of these modes, just as human language automatically writes with letters, even when the writer is unaware of grammar consciously. This gives us a new way to think about information. Earlier, when we talked about winding and topological charge, we saw how continuous fields can carry discrete, integer-valued information that is robust under deformation. Now, with spectral modes, we see how a continuous field can also carry graded, analog information in a highly structured way. The list of mode amplitudes in a region of space and time is like a data vector. It tells you which patterns are present and in what proportions. Some patterns might be almost silent, others might be dominant. Together, they encode the full state of the field. You can imagine two extreme ways of storing information. One way is local, pixel by pixel. You record the value of the field at every point separately. The other way is global mode by mode. You record the amplitudes of each spectral pattern. In practice, these are just two different coordinate systems on the same space of possibilities. The Holophase language is comfortable in both. It can talk about local derivatives and about global modes. It can move between the two descriptions as needed. This flexibility is part of its claim to be a serious candidate for a universal language of physics. If you want a simple exercise to carry with you, you can try this. The next time you hear a busy city soundscape, do not only focus on the noise as a whole. Let your attention drift and see if you can pick out recurring rhythmic modes. The regular whoosh of passing cars, the periodic beep of a crossing signal, the slow breathing of distant traffic, the occasional high-pitched cries of birds. Each of these is a mode, and the city sound is their sum. You can do the same with the visual world. The repeating windows on a building, the alternating shadows of trees along a road, the grids and curves that appear again and again in human-made structures. Little by little, you will train your intuition to see modes everywhere. When we later step into the concrete formulations of physical law, this habit of perception will serve you. You will be able to hear the model content of equations, to see when a theory is really saying this system prefers these modes and punishes those. You will recognize that many famous results in physics, from the quantization of energy levels to the stability of planetary orbits, can be heard as statements about allowed modes and forbidden modes. The Holophase framework simply makes this melody explicit and universal. And so, as we stand at the end of part 20, it is worth pausing. In this single episode, we have traveled from pure syntax to deep semantics. We started with phi as a bare map into a circle. We built its derivative alphabet. We climbed into grammar, closure, and integrability. We crossed into topology with sigma, winding, knots, and braids. We touched holonomy, where loops remember curvature. Then, in this book, we asked how meaning arises without any external reference, how intensity and action guide the field's choices, and finally, how spectral modes provide a complete abstract basis for every possible story. Seen from a great height, spectral modes are the calm, ordered backdrop behind all this movement. They are the still points in the turning world, the pure shapes that remain themselves while everything else changes around them. Phi can choose to speak softly in one mode, loudly in another, or in rich chords of many together. But beneath that freedom lies a simple fact. It has a finite alphabet of structural notes, and everything it ever says is written with them. Finally, we return to phi itself, because we must not forget the promise we made at the beginning of this journey. Spectral modes do not add new substances to the universe. There is still only one field, phi. What we have discovered is that phi's complexity can always be re-expressed as combinations of simpler forms. The abstract basis of modes is a map of all the ways phi can express itself. Each mode is a pure possibility, a specific way that phi can sing. Any actual configuration is a particular chord in that possibility space. Spectral modes are the deep alphabet of structure. They complete the abstract semantic picture. We now have a language with symbols of change, with internal meanings, with triune projections into time, space, and motion, with measures of intensity, with a principle of preference, and with a basis from which any pattern can be built and understood. We have, in other words, reached a kind of abstract completion for Episode 8. Zooming out, remember that everything we have discussed is still one field, phi, and its derivatives, the single language the universe uses to write every story. In this episode, we have explored that language in its pure form, before it writes any particular world. From here, in future episodes, we will slowly descend from this abstract height into the concrete universe, asking how these patterns become the time you feel, the space you move in, the motion you witness, and the energies, particles, and forces that science describes. For now, as you look at faces, trees, skylines, rivers, or starry skies, try to feel the hidden modes within them, the pure tones of structure quietly superposed to create what you see. In doing that, you begin to sense reality as the Holophase framework describes it, not as a chaos of separate things, but as a symphony of modes played on one continuous field of phase. Salam and peace be upon you.